Howdy. So what have we learned so far? We've learned that the change enthalpy of a reaction can be calculated using standard enthalpies of formation by doing products mass reactants. We've learned that the amount of heat absorbed by a reaction under constant pressure, assuming no expansion work, is equal to the change enthalpy of the reaction. This video is on Hess's law. Hess's law gives us another way of calculating the change enthalpy of a reaction, and hence the amount of heat absorbed or emitted by a reaction. Hess's law can help us understand complicated processes by breaking them up into smaller steps. And so after this video, you should be able to describe Hess's law, what it means. You should be able to use Hess's law to calculate the change enthalpy of a reaction, given the change enthalpy of other reactions. So Hess's law says if a reaction is carried out in a series of steps, the change enthalpy for the reaction will be equal to the sum of the change enthalpies for the individual steps. So for example, if we're starting with methane gas plus oxygen gas, and we're going to CO2 gas plus liquid water, we could imagine two different pathways. One this way, where we go to CO2 gas plus H2O gas, and then where you convert the H2O gas to H2O liquid. Or you can imagine one-step pathway where you go straight from the methane O2 gas to CO2 and the liquid water. Now, enthalpy is a state function, and so it only depends on the final initial states. And so this is our initial state, this is our final state. The delta H should be the same if we take this path or that path. Remember, enthalpy is not a path function, it is a state function. And so we could actually write this path, the two-step path, into two steps as reactions. Remember that if you add reactions, you added the corresponding delta H's. So if we add these two reactions, then we add the corresponding delta H and we get a minus 890 kilojoules per mole. Now remember that things common on both sides cancel. And so when you add these two reactions, you'd end up with H2O gas, 2 H2O gas on the reactant side and 2 H2O gas on the product side. And so things common on both sides cancel. And again, delta H, or Hess's law, works because enthalpy is a state function. Now we could also look at a little bit more complicated example. So say we're starting with sodium metal and chlorine gas. And so that would be the elements in their standard state. And we want to form the sodium chloride solid. Well, and also please remember that the potential energy means less stable. And so we can calculate the energy changes in individual steps to get this entire process. But remember that the reaction does not actually occur in these individual steps. And so the first step we can think about is converting from sodium metal to sodium gas. And so that would take about 92 kilojoules per mole. Then we can think about going from the chlorine molecules to chlorine atoms. That would cost 120 kilojoules per mole. Now, if we remove an electron from the sodium, that corresponds to the ionization energy of sodium, 494 kilojoules per mole. Remember, ionization energies are always positive. Now, if we take that electron and we put that on the chlorine, that would be the electron affinity for the chlorine, and that would be minus 349 kilojoules. Electron affinity is energy released when an atom or ion gains an electron in the gas phase. Electron affinity can be positive or negative. Ionization energy is always positive. It always takes energy to remove an electron. And so now if we take the sodium ion gaseous and chloride ion gaseous and we form sodium chloride solid, we're going from something where intermolecular forces are typically negligible to a strong ion-ion interaction. And so that's why you're going from something much less stable to something much more stable. Now the lattice enthalpy is when you're going from the sodium chloride solid to the gaseous ions. And so the lattice enthalpy would be a positive 787 kilojoules per mole. But in this example, we're going from the ions to the ionic solid. And the last enthalpy is important. It actually is a measure of the strength of the ion-ion interaction of all the ion-ion interactions. And so last enthalpy is defined as the energy required to go from ionic solid to gaseous ion. Hence, last enthalpy is always positive. It's always going to take energy to go from ionic solid to the gaseous ions. The stronger the ion-ion interaction, the more stable the solid, the larger the lattice enthalpy. Now, if we add all these steps together, so we can imagine we have a pathway going this way, or we have a pathway going that way. The two should be the equivalent. And so if we add all these steps together, we get a minus 429 kilojoules per mole. So to go from sodium metal plus chlorine gas to sodium chloride solid, you would release 429 kilojoules of energy. Now, this is not how sodium chloride is formed, but it does enable us to understand the different steps involved and the different energetics involved. If a step causes the amount of electrostatic attraction to decrease, it results in a state with a higher potential energy, less stable. If it requires a electrostatic attraction to increase, like going from the gaseous ions to the sodium chloride solid, then you're going to something more stable. Now, we could also write the steps in terms of chemical reactions. And we have our delta E's here. And then if you add these all up, things come on both sides cancel, and you add your energies, and you get minus 429 kilojoules. We can look at another one. So making H2 from water involves two steps. So we go from H2O liquid to H2O gas, and the H2O gas to hydrogen gas plus oxygen gas. Now, if we add these two, remember things come on both sides cancel, and we have H2O liquid going to H2 gas plus O2 gas. Now, we're writing the heat just like a reactant because these are endothermic processes. Remember, for endothermic processes, delta H is positive, heat is a reactant. And so we can add the heat together, and for the entire process, we get 285 kilojoules per mole. And so again, Hess's law says that the change in delta H for one pathway has to be equal to the change in delta H for the other pathway. If you add reactions, you add the corresponding delta H's. Now we can equivalently write it this way, where we, instead of writing the heat as reactants, we can also write a delta H. And again, if delta H is positive, that means it's endothermic. And so you'd have that much heat as reactant. If we look at a different one, here we're asked to calculate the delta H for this reaction, knowing the delta H's for these two reactions. And so what we have to do is we have to figure out how can we add these two reactions to get that reaction. Now, sometimes we'll have to multiply a reaction times the number. And when you multiply a reaction times the number, you have to multiply the delta H by that number. Sometimes you have to flip the product's reactants. And if you flip the product's reactants, then you change the sign for your delta H. And so we have sulfur as a reactant, sulfur as a reactant. So we'll probably keep that first reaction the way it is. And here we got SO3 as a product, SO3 as a product. So we'll probably keep the second reaction the way it is. And so if we add these two reactions, we get the reaction that we're looking for. If you add reactions, you add the corresponding delta H's. And so we get minus 395.7 kilojoules. We can try another one. So given the following reactions, calculate the change enthalpy for this process. And in this one, notice that we have carbon solid here. It's the only place it's in this reaction. And we have carbon solid here. So we'll need to flip the top reaction and divide it by 2. And so we flipped it, that changes the sign. we divided the reaction by 2, so we have to divide the delta H by 2. And let's see, for this reaction, we have H2O gas, H2O gas, H2, H2. And so for the second reaction, I don't think we have to change it at all. And now if we add these two reactions, we get the reaction that we're looking for. Well, remember, things common on both sides cancel. And so if we add reactions, we add the corresponding delta H's. So 484 minus 394 gives us 90. And again, remember, if you flip a reaction, it changes the sign of your delta H. If you multiply a reaction times the number, you have to multiply your delta H by that number. Now, so we had taken this reaction, we had flipped it and divided it by 2. And actually doesn't matter in which order. So if you flip it, then divide it by 2, or divide by 2 and then flip it, you should get exactly the same answer. And so you have to look at these reactions and figure out, okay, do I need to flip it? Do I need to not do anything with it? And so typically you want to look for the unique compound. So we only had one place where we have the carbon solid here. And we saw we needed the carbon solid as a reactant. That's how we knew we needed to flip that top reaction. And they had a 2 and a 1 here. So that tells us that we had to divide that reaction by a half. So we have another one. So given these two reactions corresponding delta H's, calculate the delta H for this process. And so for that top one, we have iron oxide, Fe2O3. We have Fe2O3 here. So most likely we don't need to change that top reaction. Now for the second one, we have FeO. And notice that we have FeO down here. Now again, notice that there's only one place in these two reactions where we have FeO, and that's in the reactant of the second reaction. And so we're going to have to flip it, which will change the sign, and we're going to multiply it by 2. And so we flipped it, changed the sign, and so we go from negative 16.5 to plus. We multiply it by 2. 16.5 times 2 gives us 33. Now if we add these two, cancel the things that are common on both sides, and we end up with Fe2O3 plus CO goes to 2FeO plus CO2. When you add reactions, you add the corresponding delta H's, and so 33 minus 26.8 gives us 6.3. And so sometimes the hardest part is to figure out how you have to change the reactions. And so the change in enthalpy reaction can be determined using enthalpies of formation by doing products minus reactants, or you can also calculate the change in enthalpy by finding a series of steps that equals for the reaction that you're looking for using Hess's law. So hopefully now you can describe Hess's law. And again, remember Hess's law works because enthalpy is a safe function. And hopefully you can also use Hess's law to calculate the change in enthalpy of a reaction given the change in enthalpy of other reactions. I hope that helps.